So let's see what we know here, and because part of the challenge is kind of reading through this and knowing how to interpret what the information is that's given and what is it exactly they're asking us to find. So if water is leaking at a rate of 2 cubic feet per minute, what is that telling us in the language of calculus?
It's your rate of change.
It's a rate of change of what?
Your volume.
Yep, so it's volume per time. Okay, so it's a rate of change. So that means it's a derivative. And so that means dV dt. And because it's leaking out of there, that's making the volume of the water in the tank decrease. So we're going to call that a -2. Now the 5 and the 6 just give us the dimensions of the actual container. So those are not changing, those are fixed. So that's, we're going to use that, but not directly. Now we're asked, how fast is the water level falling? So what is that asking us to find in the language of calculus?
The derivative of the volume.
Not
Change
the
in height?
It's the height, yeah. So so we have the tank that's got a radius of 5 and a height of 6. The water inside is also forming a cone because it takes whatever shape that it's inside of. It's got a radius and it's got a height, but these, as the water leaks out, that volume and rate and height are changing with time. So we're looking for how fast is the water level changing. That's a change in the height. And so what we're trying to find is dH dt. That's our goal, is can we figure out what is the derivative of the height with respect to time. That also tells us that we want to know that at the moment that the height is 3. So you have to be careful here because you need to think, because it will vary from one problem to the next, is this height always 3, or is this a height that's changing with time and it's going to be just at a moment that we're capturing the height to be 3. And here, because as the water drains out, the height is changing, we want to remember that we don't want to plug this into our formula before we differentiate, because then that's assuming that it's a constant all the time. So instead, we're going to have to differentiate this, and then after we differentiate it, then plug in that value for the h. So when you do that, it makes a huge difference. Now, as it stands, this is our volume formula, and we're talking about the volume of the cone of water. So the radius and height are both changing with time. The volume is changing with time. If we differentiate this right now, we could do that, but we're going to have to use a product rule here, which is going to be the first times the derivative of the second, which is going to lead us to a dH dt, which is good because we want to find dH dt. But then we're going to get an h times, and then when we differentiate this, part of that derivative will be a dr dt, which we don't know. And so that would be two things that we don't know in the same problem. We could figure it out, but there's an easier and a more efficient way. And that is to try to get the radius in terms of h first. Plug that in and then differentiate where we have only one variable here that's changing with time, in addition to that volume that's changing with time. So to get the r in terms of h, we have to look back at our picture here and see that we have some similar triangles. So if you look at the actual tank itself, the radius and the height and the side of the tank form a triangle. If you look at the cone of water, the radius and the height and that side of the cone of water form a triangle that's similar to the triangle in the tank. And from your geometry days, we know that similar triangles have proportional sides. So that means we can set up a proportion between the sides of the tank and the sides in the water triangle. And so we'll get that the 5 over 6. So the radius over the height of the tank will equal the radius over the height of the cone of water that's sitting inside the tank. Does that make sense? So then we can solve for r in terms of h if we multiply that h to the other side. And so we'll get that r is going to be 5, 6h. And this kind of thing happens not all the time, but a lot of times in related rates problems, sometimes in optimization problems too. Now we can plug this into our volume formula, and we will be able to then change it into where the volume depends only on one variable, the h. And sadly, when I made this up off the top of my head, these numbers are not going to be very pretty. So the 5, 6 will get squared and become 25, 36. The h will get squared and become h squared, which will also multiply that other h. And so I guess we're going to get, if we lump all of this constant together, that's going to be 3 times 30 is 90, plus 18 is 108. And that's going to be an h cubed. Okay. So now we're ready to actually take the derivative. And notice we're not going to plug the h in yet. We're going to differentiate this first. Then we'll bring that into play. So the t is our independent variable. These are all changing with time. So we're differentiating with respect to t. So the derivative of the volume is going to be dv dt. And then we'll get that 25 pi over 108. And then the derivative of h cubed is going to be, it's a chain rule derivative, so it's 3 times h to the second times the derivative of h, which we don't really know, but we're going to call it the symbol dh dt. Now we're going to try to solve for that dh dt. We know the dv dt, we said that was the -2, so we're going to plug that in, -2. We can actually do a little bit of canceling here. Since 1 plus 0 plus 8 is 9, that's divisible by 3, so we can say 3 is going to go in there. 3 goes into 10 3 times, and that'll be 18, so I think that's going to take us to 36 dh dt. Still not pretty, but a little bit better. Is that okay? And then to solve for dh dt, we'll multiply by the reciprocal. So that 36 is going to hit that -2, and the pi is down in the denominator with the 25. So -72 over 25 pi. And the units here would be, what's it going to be? Not cubed, because now we're not a volume anymore, but it's going to be just feet per minutes, because we have a height over a time. And we can see it's a negative because it's decreasing. Okay?
What happened to the h squared?
Oh, I left that off, unfortunately. Thank you for noting that. So we need to still have that h squared there. And that's where we're going to plug in, what do we say was h? 3? Oh, look at that. That's going to make that work nicer. So that's actually a 3 squared, which can cancel with that 36. So that is much improved. So then when we multiply by the reciprocal, it's going to be an 8. Does that look better? -8 over 25 pi. Thank you. Okay. Okay. So I know there's lots of questions on this related rate stuff. Do you want to work some problems from your homework there? Or if there's any other questions, we can answer that too. I want to talk about related rates, so whatever we can do to figure that stuff out.
You can just do your homework problem.
Yeah, we can do that. Want to pick one out?
Any of them.
Anybody else have one in particular that's bothering them, or? Pick one out that looks hard.
Can we do number 6?
Yeah, can you tell me what's that?
It says a man 6 feet tall walks at a rate of 5 feet per second towards a light that is 20 feet above the ground.
Yeah, we haven't done one like this, so this is a good one to pick out. And they're asking us probably 2 questions, right?
Yeah. At what rate is the length of his shadow changing? And at what rate is the tip of his shadow moving?
These are, and even I think the questions, the first time you see one of these problems are hard to understand exactly what the difference is between those. So let's get a picture here. So we have a 20-foot light pole. And we have this person who is 6 feet tall. And is the person walking towards or away from the light? Towards. So the person is going towards the light at 5 feet per second. So when we look at this, we're going to see that there's going to be a shadow cast. So the shadow is going to be over here behind the person. So this distance right here is going to be changing as that person walks. Because as he or she gets closer and closer, that shadow is going to get shorter. So the shadow itself, as that person moves towards the light, is going to be shrinking. Does that make sense? And then we're also going to call, we need this distance right here. How far is the person from the light pole? And these are going to, those are going to meet together. There's no gap in between those. Let's call that X, because it too is changing as that person walks towards the light. So the idea is, first what we're going to do is figure out how fast is this shadow shrinking. The second question is, as this person moves, the whole shadow itself is moving towards the light, and simultaneously the shadow is shrinking. And so together, how fast does that make the tip of the shadow move? We'll get to that second. I think if we answer the first question, then it makes the second question a little bit more understandable. Okay? So what we have here, again, the key is these are similar triangles. So we have a big triangle here from the light pole all the way to the tip of the shadow, and then up here. There's a second triangle that goes from the person shadow up to the top of the head of the person. So those 2 triangles are similar. And so therefore their sides are going to be proportional. And so we can then set up that proportion. So we can say, there's many different ways you can do this. So we can say 20 in the big triangle is to, this will be X plus S in the big triangle. So this side is to this side as this side is to that side, is one way to do that. That's not the only way. So we can say, now you gotta be careful on your S's because they easily look like 5s. So 20 is to X plus S as 6 is to just S. Okay? We should back up too. Now the person is walking towards the light at 5 feet per second. Now that we have this all labeled, what is it that's telling us?
The rate of change?
Of X. So that is telling us that dx dt, now be careful here too, as that person walks towards the light, is the X getting bigger or getting smaller? So it's going to be actually dx dt is a -5. And what is it that we are looking for in part A? Yeah, we want to find ds dt. How fast is that shadow shrinking? So we would expect to get a negative value there because it's getting smaller. Okay, now back to the proportion. So we have 20 over x plus s equals 6 over s. We can cross multiply. So that's going to be 6x plus 6s is equal to 20s. We can subtract that 6s over, so we get 6x is 14s. And we can divide by the 2 and just make the numbers easier. Doesn't really matter at this point. And you could, if you wanted to, either divide the 7 over or divide the 3. I would just say at this point, let's just leave it. Now both the x and the s are changing with time. And so we can differentiate this expression, this equation, with respect to t. So the left side is going to look like 3 times, remember this is a function of time.
So
dx dt, exactly. And that's going to be equal to,
7 ds dt.
exactly. Kind of weird, but that's what we get from differentiating. Now we know the dx dt is -5, so we can plug that in. So that's going to become 3 times -5. And so that's a -15. We'll divide that 7 over. And so we're getting that ds dt, the rate of change of the length of the shadow, is a -15/7. And what does it say our units? Yeah, our units there are going to be
feet per second.
feet per second, yeah. So now, once we've figured this out, hopefully it makes the part B make a little more sense. So right now, we're saying that as that person walks, the shadow is shrinking at -15/7 feet per second. Now, at the same time, this person is moving towards the light pole. So as he moves, the shadow, even if the shadow was not changing size, as that person moved, the tip of the shadow would be moving as well. So it's moving because the person is going closer to the light pole. It's also moving because the shadow itself is shrinking in length. So the tip of the shadow is this distance right here. It's the x plus s. So to say how fast is the tip of the shadow moving is to ask what is the rate of change of this distance right here. That is, what is the derivative of x plus s? Because that's how far the tip of the shadow is from the light pole. And that is just going to be dx dt plus the ds dt. Does that make sense? And we know both of those from what we did before. So the dx dt is that -5, and we just found the ds dt to be a -15/7. So I don't know, should we just make that a mixed number, 2 1/7, and another 5? Might be easier just to call that, or I guess we could call that 57 feet per second. And that's going to be negative because it's moving towards the light pole. Okay? Let's pick another one. Is there one with a can in there or something like that? Or am I thinking of a different worksheet?
I don't see it.
Okay. Is there another one on there, a ton? All of them?
Does anyone else have a preference?
I don't have it.
Okay. We can do number 5 then.
Okay.
It says a ladder 25 feet long is leaning against the wall of the house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. The first question is, how fast is the top moving down the wall when the base of the ladder is 7 feet, 15 feet, and 24 feet from the wall?
Okay. So let's start with this. So we've got our ladder and it's leaning up against the house. And so the ladder itself is 25 feet. And let's see, we want to eventually know how fast is so let's name the variables here. It looks very much like an XY axis. So I think it makes good sense to, call this distance, how far the foot of the ladder is from the base of the wall, to call that X. And how far the top of the ladder is up on the wall there from the ground, to call that Y. So then if we can name those things, now it says the base of the ladder is getting pulled out. This is like, ever been on a ladder and a friend of yours wants to play and pull the bottom out? I used to do a painting. I've been in that situation. Ha ha. So as you pull this out, so if they're pulling the base of the ladder up, or if it's slipping out, we'll not attribute this to a friend of yours. So if the base is slipping out at 2 feet per second, what's that? What are we going to call that? What is it? dx/dt. And is that going to be a positive or a negative? Positive, because it's making that x bigger. So this is telling us that dx/dt is equal to 2. And we want to know how fast is the top moving. So as the bottom starts to slip away, then of course that ladder, the bottom slides down. So what we're looking for is how fast is the top of that ladder moving down. What are we going to call that? That's dy dt. So we're looking for dy dt. Now, as you do this problem, I'll just do the first one, but you should really do all of them because if you've had real life experience, they don't move at the same rate. And it's kind of crazy because as you start, even if this is moving at the same rate, you start out moving kind of slow. By the time you hit the ground, you're really moving. So funny. Anyway, so what's the relationship between x, y, and 25? Let's put that ingredient there, yeah. So we're going to get x squared plus y squared is equal to 25 squared. 25 squared is 625. Oh, and we should say in part A, we want to know how fast is this moving? What is the dy dt when it's 7 feet from the wall? So that's going to be, what's that telling us? It's not a rate of change. Yeah, it's just the value of x is 7. So this is just x is 7. But remember, x and y are both changing with time. So we want to differentiate first, then we'll plug in the 7 for the x. So as you look at this, x and y are both functions of time. And so we'll differentiate with respect to t. So the derivative of x squared is going to look like 2. There you go, right. So it's a chain rule derivative because it's really an x of t that's in there. So it's 2x to the first times the derivative of x, which we're going to call dx dt, plus
2y dy.
Nice. And I'll get the derivative of 625. So the derivative of a constant is 0. And then because we can, we just divide out the 2's and get rid of some of the clutter because they're not really doing anything for us, just to make things simpler. now let's see if we can figure out what we know and try to solve for what we don't know. So the x we said was 7. The dx dt we said was 2.
We need to plug in 7 in the problem.
Yeah, we have to solve for the y. So going back to our original Pythagorean relationship, that x squared plus y squared equals 625. When the x is 7, we're going to get 49 plus y squared equals 625. So that means y squared, if we subtract 49 from 625, we get 576. Of course, everybody knows that the square root of 576 is 24, right? So, and we only want the positive answer because we're not going to have a height of a negative. So then our y is going to be 24, and we're trying to solve for the dy dt. So we can subtract that 14 to the other side. And our dy dt is going to be negative 14 over 24. Well, I guess we can reduce that to negative 7/12 in this feet per second. And we were expecting that to be a negative because that y value is getting smaller as the ladder slides down the wall. So this is like a fun ride at this point. By the time you get to the ground, it's not fun anymore. Others, let's do another one. Sometimes you just need to practice and see some of these done. So this is what I had in mind for today.
First one, see.
What? You want to see it?
Sure.
What did you say?
You pick it.
No, I picked the other one.
Oh, you know what to pick.
Someone pick a random.
You can't go wrong, any of those.
Number 2.
Two.
Number 2,
Okay, do that.
Okay.
The radius of the sphere is increasing at a rate of 2 inches per minute.
2 inches per minute.
Yep. Find the rate of change of the volume when the radius is 6 inches.
And this is a sphere.
Yeah.
And we know the volume of a sphere is 4/3 pi r cubed. So if they say the radius is increasing at 2 inches per minute, what's that telling us?
dr dt is 2.
That's a dr dt. It's going to be a positive 2 since it's increasing. And we want to know how is the volume changing. So what we're looking for is dv dt. And that's going to be at the moment the radius is 6. So we've got this sphere and it's going to be growing at a rate where the dr dt is increasing by 2 inches per minute. And then we want to know how fast is that volume changing right at the moment that the radius is 6. All right. So what do we do?
Find the derivative of the volume equation.
Yep.
dv dt equals.
Okay, so dv dt equals
4 pi r squared dr dt.
And was that Evan or Gavin or somebody that said earlier? So when you differentiate a volume, what you get is an area. I don't know if you're familiar with your formulas. This is the volume of a sphere, and 4 pi r squared is the area of the sphere. So in a sense, you're going to think of, I think if you think, a good way to think of it is, you have this volume that's going to grow, and if you say, what does it grow just in a little microsecond? It's going to add just like a layer, which is like adding an area of really thin thickness. That's how much volume is going to get added to that in layers. So the rate of change is an area times dr dt. All right, what next?
Now we can plug in 6 and 2.
Okay, so we're looking for the dv/dt, and we said the radius was 6, and the dr/dt we said was 2. And so we become human calculators. So 6 squared is 36. And the question is one order better than another for doing these? I don't know if much matters. You know that 4 times 36 is 144. Times 2 is 288. 288 pi. And what would our units be on that?
Inches per minute.
It's a volume.
Oh, inches cubed.
There you go. Okay. Where's our confidence level? We ready to get up and try one on the board? Do you guys have those worksheets, or do you need a hard copy of them? Hard copy? I think I got some here somewhere. Pick one out there.
Here, I'm going to for old time's sake.
I know. Been a while.
I have him somewhere. Where? Oh, that's cool. Let's see if I put him in there. I printed out a bunch of how they go.
I wouldn't do it. Yeah.
Yeah, what are you doing? Yeah. My dad goes to the garden.
Oh, really?
He just gets on it.
It's
I've
just
had
so much more work.
because he hasn't paid for any of them. He's supposed to pay for all of them. So he doesn't pay
Also
for
really
for it. So like,
Here's a
and
couple.
also
Pick one out. I know I got
why
one
did
on
it
those
hurt
search
so
for
much?
someone. Pick one out, you guys can get going in a row.
Yeah, straight to my face. I was like, what?
Student number 3.
I almost got my point left. I was so mad.
Oh, we work on the same whiteboard.
Yeah. So I'm gonna go over there.
Oh, you're good. You're good. Oh, okay.
Yeah.
So your mom.
Yeah.
About where you got from. So where is she here?
Yeah.
Oh, sorry.
My mom's came back there in Nation when she was in college. Yeah. Yeah.
So we're gonna work on number 3
Yeah.
on that worksheet. So we said that, I'm gonna try to do this for the video here. We were told that the diameter is 3 times the height. So that means that the radius is 3/2 h. And so our volume formula becomes 1/3 pi. It's gonna be 3/2 h squared. So that's gonna become, we got a pi over 3, that's gonna be 9 fourths. H squared times h is h cubed. we can at least make the numbers a little more manageable for now
The distance from
to get to here. We'll differentiate that with respect to t. So we'll get dv dt is going to be 9 pi over 4 squared dh dt. And I think we were told the height is going to be 15, and we're looking for, the height is going to be 15, we're looking for dh dt, and I think we were told dv dt is 10. So that's going to make this be 10. We've got 9 pi over 4. 15 squared is 225 times dh dt. If we divide both sides by 5, and we're going to get 9 times 45 is 405 pi. So our dh dt multiplied by the reciprocal is going to be, I don't remember what the units were, I think feet per